students, welcome back. This is Torres, elbow bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email, and I promise to do whatever I can to try to help. So lucky you get to hear my voice for another lecture. But the best part is we will be doing another example of how to use the 4 steps of hypothesis testing for proportions using a z-test. Yay! Before we start today's example, let's quickly review the 4 steps of hypothesis testing. The first step is to state your hypotheses. You're going to state the null hypothesis and the alternate hypothesis. The null hypothesis describes the status quo. It is what is believed to be happening in the population and what would continue to happen if there is no change. The alternate hypothesis describes the question. In both instances, the null and the alternate must be written in terms of the population parameter. So if you're working with proportions, you're going to use the notation of P. If you're working with means, you're going to use the notation of mu. The second step is the prepare step. This is usually the longest step. In this step, you're going to do things like choose the significance level, decide what kind of test you need. Do you need a test that is looking for any change, for values that are significantly lower than the mean or proportion, or values that are significantly greater than the mean or proportion? You're also going to look up your test statistic that describes the z-score for your significance level for the test that you chose. If necessary, you need to check the requirements to make sure that your data is normally distributed. In this step, you will also calculate the standard error. This is also the time where you should draw your model and section out the areas of rejection and the area of retention. In the compute to compare stage, you're going to be calculating your test statistic for your sample. In these scenarios, you will be calculating your z obtained in this step. You calculate your z obtained by using the z-score formula that takes the sample information. From that, you're going to subtract the population information and divide that number by the standard error. That will give you your z obtained. You will need to use technology to find the probability of the z obtained. If the probability of your z obtained is less than your stated alpha, then you should reject the null hypothesis. If the probability of your z obtained is more than your stated alpha, then you should retain the null of no difference. The final step is to interpret your results. In this step, you're going to make a decision on whether you're going to reject or fail to reject, in other words, retain the null hypothesis. You should state your conclusion in the context of the study. Today's example is dealing with dog vaccinations, because you know I love dogs. So I had to give them a shout out. The question says, the rabies vaccine for dogs can save your dog's life. If your dog bites another animal or is on the receiving end of a bite, the vaccine can protect them from a dangerous and potentially fatal illness. Furthermore, in most places, the rabies vaccine for dogs is legally required. The question asks, have more than 70% of all dogs had their rabies shots? 592 of 800 dogs examined had their rabies shots. Risk no more than a 10% type 1 error. All right, we can do this. As always, I've gone ahead and pasted the steps to null hypothesis statistical testing at the top, and then also pasted the question that we're about to answer at the bottom. I want to go ahead and keep the same colors that I've been using so that perhaps of the steps you'll remember the colors. And if you recall, green is the color that I've been using for hypothesize. Red is the color that I've been using for prepare. This magenta pink color I have been using for compute to compare, and then I've been keeping interpret in black. Okay, let's see what we've got here. Let's read the question again. The rabies vaccine for dogs can save your dog's life. If your dog bites another animal or is on the receiving end of a bite, the vaccine can protect them from a dangerous and potentially fatal illness. Furthermore, in most places, the rabies vaccine for dogs is legally required. Okay, so it seems like that first little short paragraph is just some background information so you kind of get an idea of why we're doing this at all. And then it says, have more than 70% of all dogs had their rabies shots. 592 of 800 dogs examined had their rabies shots, risk no more than a 10% type 1 error. Okay, so in the second little paragraph, what it's doing is it's telling you that they're interested to know if more than 70% of all dogs have had this rabies shot. And they did some study. They took 800 dogs, looked at their, I guess, their vet records or whatever, and determined if they had had their rabies shots, if there was documentation of their rabies shots. And a certain percentage of those dogs had their rabies shots. And then they want to know, can you answer this question, have more than 70% of all dogs had their rabies shots, by risking no more than a 10% type 1 error. Okay, so the first step, as we know, is the hypotheses. And the null hypotheses and the alternate hypotheses need to be written. The null hypothesis is the status quo. So if nothing changes, what do we expect to see in the population? And as we can find from this question, they're assuming that the population is about 70% compliant with dog vaccinations. So of all the dogs, approximately 70% have their vaccinations, and they seem to want to know if that has changed. And they're not concerned with there being less than 70%, or just a significant difference than 70%. They want to know if there is more than 70% of all dogs that had their rabies shots. So my alternate hypothesis is going to be, is P greater than 0.70? And this greater than comes from the word more in more than 70% of the dogs. So that would be the first part of this problem, is writing down the hypotheses. We can't just start going straight to prepare and writing things down. We have to know exactly what type of test we're doing. And as a reminder, one of the reasons why is because we want to eliminate any bias. And so by really focusing in on what the question is asking, instead of just looking for whatever we can find, here we've moved towards eliminating that bias. The next step is to prepare. And we can do this a variety of ways. I like to start by going ahead and writing out some of the pieces of information that we have already been given. So first thing I can do is I can write out my p-hat. And my p-hat is the proportion that we see in the sample. So that's going to be 592 divided by 800. Make that 8 a little bit better. And I'm going to go ahead and grab the calculator again. Here, 592 divided by 800, and I get 74%. So that is 0.74. Okay, I know that there is a sample of 800 dogs, and they're telling me that I have to risk no more than 10% type 1 error. So basically it's saying that my alpha needs to be no greater than 10%. So I can go ahead and write 10% like this. Okay, so the next thing I need to do, and I'm going to scooch this up just a little bit, next thing I need to do is I need to check my assumptions of normality. Okay, I'm not told that this is normally distributed, so because it doesn't tell me that, I need to see if the conditions of the central limit theorem will apply. So the first condition is that I need to make sure that my sample was randomly and independently drawn. And actually, as I read this, it doesn't say anything about random and independent sampling. So I'm just going to go ahead and put a question on that right now, so that if we proceed with the tests, we can at least say it would be necessary to confirm that this was a random and independent drawing. So I'm going to go ahead and put that as a question mark for now. The second one is that we need a large population. And the population, N, has to be bigger than 10 times the sample size. So big N has to be bigger than 10 times 800. And 10 times 800 is 8,000. So I need to know that there are at least 8,000 dogs that we're discussing here. And I'm assuming that this is for some sort of county or maybe the whole United States. It doesn't really say, but 8,000 dogs isn't really very many dogs if you think about it, especially if we're talking about this being a nationwide study or even a statewide study. So I'm going to go ahead and say that it does meet the condition of a large population. The last one is we're looking to see if it meets the condition of a large sample. And for that, our successes have to be greater than 10. And our failures have to be greater than 10. So it said that 592 dogs were vaccinated. So those would be my successes. So 592 is my successes. Is that number greater than 10? It is, so that checks out. And if there are 592 that were vaccinated, and there's 800 total, then the difference would be how many were not vaccinated, and in other words, we can call those the failures. So I would just take 800 and subtract 592, and I'm going to get 208. And then I can say, is 208 greater than 10? Yes, it is. So it meets the condition of the large sample. Now, this is all dependent on whether this is a random and independent sample and whether there are 8,000 dogs in the population. So if these two things can be said about this experiment, then it would be okay to assume that there is a normal distribution here and we can proceed with the test. But it's very important that these two things be clarified before anything in the test is actually applicable. We can only proceed with that in mind. Now that we've checked for the assumption of normality, we can continue with our preparations. And the next thing we should probably do is decide what kind of test we want to use. So remember, going back here to the hypothesis, the null hypothesis is that there has been no change from this originally projected proportion of 70%. And our alternative hypothesis seeks to determine if that proportion has increased, right? If the true population proportion is greater than 70%. And so really what we want is just everything that is to the right of the curve, right? So if here is our 70%, we want to know this stuff that's all the way up here. We don't care what's lower, significantly less than 70%. We don't care if something is either lower or greater than 70%. We're just concerned in knowing if the proportion has increased. So we want to know the more than, okay? So because we want to know more than, or an increase, or greater, then we're really just worried about this right tail. because that's where something is going to appear if it is much greater than 70. It's not going to be down here. That doesn't make any sense. So we're going to need a one-tailed test, but specifically, we need a right one-tailed test. Okay, so we're going to need to find the ZCrit that is going to be positive, right? Because the z-scores that are greater than the mean are positive, and we've got to figure out what that is. Okay, so we've got to go to our ZCrit table, and we've got to find what that ZCrit is, so that 10% of the curve is to the right of that line. This time, the whole 10% is going to be over here. Unlike the last few examples that we did where we were looking for any change and that alpha had to be split up equally, this time we're just looking for that whole 10% to be in the right tail. Whole 10%, or the alpha, is going to be in the right tail. Okay, so we need ZCrits. We need a right one-tailed test. So here we are, right one-tailed test, and I'm going to go ahead and make this a little bit bigger. So here's my right one-tailed hypothesis test for z-tests, and I need 10%. So 10% of the curve is going to be at a positive 1.282 z-score. So my ZCrit is positive 1.282. And I'm going to go back to my Ziteboard, and my tcrit is going to be positive 1.282. Okay, here's my ZCrit. Okay, so let's draw this out. I'm just going to draw a brand new one over here so that we can have it for reference. I'm going to make it a little bit bigger because sometimes it gets full of stuff. Okay, here is my normal curve, and I'm going to go ahead and draw out my standard deviations. I'm going to go ahead and put z-scores, I should say, at the top. So this is going to be 0, 1, 2, 3, negative 1, negative 2, negative 3, and my ZCrit is going to be positive 1.282. So here's 1. This would be about 1.5. So I'm going to say that positive 1.282 is right about here. That's where I'm going to kind of guess at it. Okay, this is going to be positive 1.282. If anything is greater than that, we are going to reject the null. And if anything is less than that, we are going to retain the null. Okay, and everything from here over is 10% of the curve. Okay, so all this right here is 10%. So we've got our lines marked out. I think the only thing we need to find now is we need to find what our standard error is. So let's go ahead and calculate that. And we can use the standard error formula for proportions, which is just the square root of the sample proportion multiplied by a whole minus the sample proportion divided by the size of the sample. And I have already written these out, so it makes it really super nice and easy for me to just copy everything down. So we know that p hat is 0.74, and I'm going to multiply that by a whole minus 0.74 divided by my sample size, which was 800. And I'm going to go ahead and use Google Calculator to do this calculation. I'm just going to kind of put this right here. I'm going to clear this out, and let's see what I've got. I've got 0.74 times parenthesis 1 minus 0.74 equals, and I get the numerator of this fraction. Now I'm going to go ahead and divide it by the 800 that is in the denominator that represents the sample size. and I'm going to get 0.0002405. I'll go ahead and write that down. So I'm still here as 0.0002405. Okay, now I still have to take the square root of this. So what makes it kind of nice when you're using Google Calculator is instead of writing this all out again, you can just hit the square root key and then see this key right here that says ANS. That is the last thing that you calculated. And you can even check right here, see how it has ANS equals 0.0002405, the same thing that we had calculated. I can just hit answer and it helps me to avoid to put in extra stuff in there. So that is going to be my standard error, and my standard error is 0.01550. Fantastic. Okay. Now, if I were going to go ahead and compare this, I'm just going to go ahead and round the standard error. Remember, I just did this the last time just for the sake of making things simple. I'm going to go ahead and round this to about 0.02. Okay? And let's see what this means in terms of the proportions up here. Okay? And I'm going to just make a little dotted line here. That's my 2, my 3, my 0, -1, -2, -3. And right here, my 0 is going to be the population proportion, so 0.7. And this distance is going to be approximately 0.02. So if I continue adding this, the 0.02, I'm going to get that this next line right here is going to be 0.72. And the next one is going to be 0.74. And the next one is going to be 0.76. And in the opposite direction, I know that this one is going to be 0.68 and 0.66 and 0.64. So if I line up what my ZCrit is, I'm going to get a proportion raw score of about 0.725. I don't know, something like that. Something like that. Okay, awesome. All right, let's see what we're going to do here. We are now finished with the prepare step. So we're going to go ahead and move to compute and compare. So now we figure out what our Z obtained is and what our probability is of getting that Z obtained, and compare it to our alpha and to our ZCrit. So you know how I like all the colors to match. I've gone ahead and just tried to organize this a little bit since you last saw it in the prepare stage and make things approximately about the same size. And we're going to go ahead and go into the compute and compare part of the testing. And we want to first find what our Z obtained is. So our Z obtained is going to have the formula of P hat minus the population proportion divided by the standard error. So my Z obtained is going to be 0.74 minus 0.7, and we're going to divide that by the 0.01550 that we calculated in the prepare part. Once again, I'm going to bring over my handy dandy Google Calculator to help me with the calculations. And I'm going to go ahead and type in, I'm going to clear this out, 0.74 minus 0.7, and I get my numerator, and I'm going to divide that numerator by the standard error, which is 0.01550 equals, and I get a Z obtained of 2.58. So my Z obtained equals 2.58. And of course that is positive. Okay, this is looking good because we just had to get to 1.282. I wonder what happened to my 8 here. Write that puppy back down. 282, right? We just had to get to this z-score in order to be able to reject. So at this point, 2.58 is right over here, and that is in the area of rejection. So this is looking really, really good to reject. This is positive 2.58. Okay, now the next thing we need to do is we need to make sure that the probability of committing a type 1 error is less than the alpha that was stated to us originally of 10%. And for that, I need to go to the probability calculator. If you recall, there is a free probability calculator in the description box, and when I click that, I get to this normal distribution calculator. And as a reminder, this one has a default of mu and standard deviation, but we're actually going to use p and the standard error. So we're going to here put in p what we expect the population proportion to be, and that's going to be 0.7. And our standard deviation is going to be what our standard error was that we calculated. And if you recall, and I'll just go over here real quick, remember that was 0.01550, and it's right here as well. Okay, so 0.01550. Okay, and we want to know what is the probability of p being greater than 0.74, okay, which was our expected population proportion. I'm going to go ahead and hit compute. Look at this right here, and this right here, it's saying the probability of getting a score that is greater than 0.74 is 0.0049. And as you can see over here, this is a very, very tiny amount. This is a very, very small amount. Now we had set the alpha at 0.1, and because this probability, the probability of getting that p-hat is smaller than the probability that we were willing to risk, which was the 10%, our stated alpha, then we have enough evidence that we can confidently reject the null hypothesis. Because this is saying that if you reject the null hypothesis with this proportion of 0.74, you're only going to be making an error less than 1% of the time. And you were willing to make an error 10% of the time. So this is much, much less of a risk. So I'm going to go ahead and bring up this, and I'm going to put down that the probability of getting a z obtained of 2.58 is 0.0049. Okay, and since this is less than 10%, which we were willing to risk of committing a type 1 error, then we can reject. Yay! Because we're right here, we're in the area of rejection. Okay, far over in the area of rejection. Awesome. Okay, so we computed and then we compared. And that is the third step. Okay, now finally comes the last step of writing this in context. And remember, we have to write this in context in a way that it lets the reader know, listen, this is what we think is happening, but keep in mind, we don't have any evidence that this was randomly drawn or if it was independently drawn. And really, we don't know how big the population is that we're comparing it to. So assuming that the study meets that criteria, we can say with a great deal of confidence that this proportion in the population has increased. The last step is to reject or to retain the null hypothesis and to state the conclusion in the context of the study. So for that, we can say that assuming that the sample was selected randomly and independently, and the population of dogs for the study is presumed to be greater than 8,000 dogs, then the results show that there is a statistically significant increase in the proportion of dogs that have received the rabies vaccines. So for this scenario, it said that the rabies vaccine for dogs can save your dog's life. If your dog bites another animal or is on the receiving end of a bite, the vaccine can protect them from a dangerous and potentially fatal illness. Furthermore, in most places, the rabies vaccine for dogs is legally required. They want to know if more than 70% of all dogs have had their rabies shots, and they took a sample of 800 dogs. 592 of those dogs had their rabies shots, and they wanted us to risk no more than 10% type 1 error. Okay, so the first thing we did was we wrote down the hypotheses, and in this, the status quo was presumed to be 70%, and so that was our null hypothesis, and that's what we expect to see in the population unless there's been a change. And the researchers or the vets or whoever this was interested in knowing if that amount had increased significantly. And so we wrote the alternate hypothesis as P is greater than 0.70. Okay? All right. Next step. The prepare phase is often the one that takes the longest because, there's a lot of stuff to check. And so we started off by just writing down some of the stuff we knew. So we wrote down like the p-hat and figured out that 592 out of the 800 was 74%. So that was going to be our p-hat. The size of the sample was given and it was 800. And our alpha level is what we risk in committing a type 1 error, and they wanted us to commit no more than 10% alpha. So we wrote down alpha as 10%. The next thing I did was I checked for the assumptions of normality, and since the question did not tell us if this was normally distributed, we had to use the central limit theorem to check. So the first thing I checked for was to see if the sample was random and independently drawn. And there was no information in the scenario that said that either way. So we went ahead and I just put a little question mark on it so that I would remember that I would have to address this at some point. The next part is we talked about, is the population large enough for us to be able to meet the condition of a large population? And we know that the population has to be at least 10 times as big as the sample size. And since the sample was 800 and 10 times 800 is 8,000, in order for the central limit theorem to apply, the population of interest has to be greater than 8,000. And since the scenario did not talk about how big this population was, like whether this was a statewide sampling or a county sampling or, a nationwide sampling, we don't know. So again, I had to make sure that I would talk about that being a condition in order for anything that we did here to be valid. The last one was the condition of a large sample, and we needed to make sure that the successes and the failures were greater than 10. When looking at the successes, there were 592 successes, and of course that number is larger than 10. And if there's 800 dogs and 592 of them have rabies shots, then the difference of 208 would be dogs that do not have rabies shots. And since 208 is greater than 10, then we know that it meets that condition of the central limit theorem. So at this point, assuming that we have a random and independent sample and that the population is greater than 8,000, we are good to go. Next, we decided that we were going to look at what type of tail we were going to need. And since the hypothesis is concerned with a proportion much greater than what is expected, and not less than or either less than or greater, then we had to look at a right one-tailed test. And since the alpha level was 10%, we needed to find out what the ZCrit would be for a right one-tailed test when the whole 10% is going to be in the right tail. So we would need a positive z-score to mark that border of reject and retain. And by looking in our ZCrit table, we know that that number z-score is positive 1.282. And we went ahead and drew a normal distribution, and we said, okay, well, here's 0 and here's 1. So 1.282 is going to be, just a little to the left of center between positive 1 and positive 2 z-scores. And that's where we're going to make the line. If we get a z-score that is greater than that, we're going to go ahead and see that as enough evidence to reject the null of no difference. And if we get a z obtained that is less, then there will not be enough evidence for us to reject the null, and we will have to retain it. The last thing we did is we went ahead and calculated the standard error using the standard error formula, and we went ahead and just marked off a little proportion line, and we figured if we had a proportion of greater than approximately 0.725, and we know it's going to be 0.74 already, then we're probably going to reject. So right now, it's at this point, it was looking very good that we were going to reject. The compute and compare obviously has two parts, compute and compare. So in the compute part, what we did is we computed the z obtained, and we took the p-hat. From that, we subtracted the population proportion, and we divided that difference by the standard error, and we got a z obtained of positive 2.58. Also, we calculated the probability of getting that z obtained, or that z-score, or greater. And then the compare phase is we're going to compare these two values that we computed to our ZCrit and to our alpha. Our ZCrit was positive 1.282. And since 2.58 is more than that, that is telling us that we are in the area of rejection and we can reject. The other way that we checked it is that we wanted to make sure that the probability of getting that z obtained is less than we were willing to risk, and what we are willing to risk is the percentage that we've set as the alpha. The alpha was 10%, so 0.1. The probability of getting a z-score greater than 2.58 is 0.0049. So since this probability is less than the 10% that we were willing to risk, then we have enough certainty that there is some phenomenon happening with the sample that we can reject. The last step, we are going to state the conclusion in the context of the study. And we have to remember that there were a couple conditions that we had to make sure that were met before anybody could take this as some indication that there's been a change in the proportion of dogs getting vaccines. So we wrote, assuming that the sample was randomly and independently selected, and the population of dogs for the study is greater than 8,000, then the results show that there is a statistically significant increase in the proportion of dogs that have received their rabies vaccines. So what did I do here? I let them know that these two things have to be in place, but if they are in place, then there is enough evidence, then we can say with a great degree of certainty that the proportion of dogs that have received their rabies vaccines has increased. And now we've gone through all the steps of null hypothesis statistical testing for proportions using z-tests in the scenario that dealt with dog vaccines. So what's the big idea? Today's big idea is that the 4 steps of hypothesis testing provide a systematic process to answer a research question concerning the population parameter. The 4 steps are hypothesis, prepare, compute, compare, and interpret. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay, this is your teacher Torres saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!